What is going on, guys? Welcome back. In this video today we're going to learn how to implement k-means clustering from scratch in Python. So let us get right into it. Alright, so we're going to implement the k-means clustering algorithm from scratch in this video today. And we're going to start here with a theoretical background first, so understanding what k-means clustering is, how it works, how it is computed mathematically, what the different steps are, and then we're going to put all of this into Python code from scratch, meaning we're only going to use NumPy so that we can work with arrays efficiently, but we're not going to use any machine learning modules or packages like scikit-learn, for example. We're going to use core Python and NumPy. So we're going to get started here briefly with a theoretical part. So I'm going to open up my paint here. And I think a lot of you guys will probably have an idea of what k-means clustering is, or at least what clustering is. It is an unsupervised machine learning algorithm, meaning we have unlabeled data and we try to find clusters in that data. Now, maybe you know what classification is. So classification, we already implemented the k-nearest neighbors classifier from scratch on this channel. Classification is I have some data points here, let's say in 2 dimensions. And I know, for example, that all of these points are the red class. And I know that all of these points here are the yellow class. And I know that all of these points here are the turquoise class and so on. So I already know what these points are. And then I get a new point, for example, this one here, and I don't know what it is. And I ask my model, which in this case would be very easy to answer, which class does this probably belong to? And then k-nearest neighbors would tell me, okay, this is probably turquoise. So I classified it. Now with clustering, we have a slightly different approach because we have no labels. So in clustering, we have still data points here again in 2 dimensions, but they are unlabeled. So they're not having a class assigned to them. And of course, real data doesn't look like that. First of all, real data is oftentimes high dimensional, but also not that well separated. You will usually not find data where you can find clusters so easily. You will oftentimes have more chaotic data, more noisy data. But that would be clustering right here. So I don't have any labels here, but I want to find clusters. So I want to end up with cluster 1, cluster 2, cluster 3. Now I don't know what these are, but I know that they're separate clusters. I detect the clusters here. And k-means clustering is essentially a method to do that. So what we do with k-means is we define how many clusters are we looking for. This is the k here. So k clusters is what we're looking for. In this case, for example, we could try to find 3 clusters, which would be a very obvious example, but we could also try to find 5 clusters or 2 clusters. It doesn't matter. We can define k how we want. Of course, there are strategies to choose k efficiently. You can try to evaluate different k's with certain metrics. This is beyond the scope of this video here. I can make another video on that in the future, but there are strategies on choosing the correct k, but essentially you just choose a k based on whatever strategy you have. So for example, we could say we're looking for 3 clusters here. And how do we find these clusters here mathematically is we initialize the centroids, so the cluster centers, randomly. So I can say, okay, the first cluster has its center here, which of course doesn't make sense because there's no data here. Then the second one has the cluster center here. And the third one has the cluster center here, for example. Just randomly. It could also be all of them down here. Doesn't matter. Now, those are just randomly initialized centroids. And what we can do now is, or what we do in k-means is, we calculate for each data point here the distance between these cluster centers. So I take this point here, for example, and I calculate the distance to this yellow centroid. And I do the same thing with the turquoise centroid. I do the same thing with the red centroid. And I do this for every single data point. So I compute the distances here. And then I say, okay, which one of those 3 centroids is the closest to this point? And I say, okay, in this case, it's the yellow one. So this point will now have a yellow class, you could say, or this is part of the yellow cluster. And maybe all of these are part of the yellow cluster here. Maybe some of these here are actually part of the, where's my turquoise? Some of these might be part of the turquoise cluster down here, maybe. And those are again yellow. then all of these are probably going to be red, and all of these are going to be turquoise, right? So that is the first step. Now, the next step is we take the centroids with these assignments that we have now. So knowing that these are now red, knowing that these up here are yellow, some of these are turquoise, down here we have only turquoise. We take the centroids and we reposition them at the mean position between all these points. So for example, for yellow, since all the yellow points are here, the new yellow centroid would be probably here in the middle. Now for red, it's quite similar and quite simple as well. We put red in here. This is now the new cluster center. This one does not exist anymore. And this one does not exist anymore either. For the turquoise one, we cannot just put it down here, even though we know that this would be a correct solution here, or the desired solution at least. But we do have some turquoise points up here. So we put it maybe somewhere here. So closer to this one because we have more data here, but we still have some data here. So we put the centroid here in between. So that is one iteration. What we do next is we do the same thing. We take every data point, we calculate the distance between all the centroids. So I take this data point up here, for example, and I ask how far away is it from turquoise? This far away. How far away is it from this yellow point here? This far away. Okay, how far away is it from the red point? There you go. Okay, so now all of these would become yellow. And these would stay red, these would stay turquoise, and then we again reposition the centroid. So now we have no turquoise points up here. So the turquoise centroid would be down here. And we do this as long as we, or until we reach the max iteration number. So we can say, okay, do this a maximum of 200 times. So do it less or equal to 200 times. Or we can also abort earlier if there is no change. So if I already have this result here, I can run this for 1,000 times. These centroids won't move a lot. If they will probably not move at all. So this would also be a reason to stop. So either because you reached a max iteration or because there's no change happening really. And that is the basic idea of k-means clustering, and this is what we're going to implement in Python now. So as I mentioned, we're going to need NumPy, so pip install NumPy if you don't have it on your system, and we're also going to install matplotlib. Now, matplotlib is just for visualization, so it doesn't help us to implement anything, so we are going to use it. NumPy, matplotlib, and then we're going to say import NumPy as np, import matplotlib.pyplot as plot, and then we're going to create a class called k-means clustering. And we're going to say that we want to have a constructor where we're going to set the k. So we're going to set the k by default to 3, but we can also change it when we create an instance of this class. So self.k is going to be k, and self.centroids in the beginning is going to be none. So we don't have any centroids yet. Now, all of the magic is going to happen in our fit method. So for the fit method, all we want data points. Because again, remember, we're doing unsupervised learning. We don't have x and y. We don't have a target variable. We only have data that we want to cluster. So we want to have x as an input here, and then we want to have a max iterations. Let's say 200 here. What we do now is exactly what we said. So just remember what we drew here now. Maybe you cannot really, maybe what was a good image, something like this here. What we do is we randomly initialize the centroids first. This is the first thing we want to do. So we say self.centroids equals, and we're going to use NumPy to generate random centroids. Now, you have to do this intelligently, or you don't have to, but it's reasonable to do this intelligently. Let's say here, maybe I will move this a little bit. So let's say I have a coordinate system here for my data that goes from 0 to 200 on the x-axis, or on the x1 axis, we could call this. And it goes from -5 to 5 on the y-axis, or on the x2 axis. If I randomly initialize the centroids, I don't want to just pick any random position between 0 and 1 or between 0 and 200. For each axis, I want to have a random position within the min and the max of the data. So if I have data points here, and here, and here, and all that. I don't want to generate a random centroid up here because it's going to be wrong, definitely, because there is no data up there. So I want to keep the centroids in the boundaries of the data that I already have. So what we're going to do is we're going to say NP random uniform. A uniform distribution is just you give it a min and a max, and every value in between is equally likely to be the result. So we're going to pass for every single dimension of our X data the minimum and the maximum for the respective dimension. So we were constantly talking about 2 dimensions here. You can also do k-means clustering with 3 dimensions or with 10,000 dimensions. So if I have 3 dimensions here, I would have maybe X, Y, and Z. Then I would have a data point here. And every single axis here has a min and a max. And this, of course, means that that this is also the case for 5,000 dimensions. Now, we cannot really visualize that, but for 5,000 dimensions, you would also have 5,000 different min-max ranges. So we're going to say here NP random uniform, and then we're going to say NP a min. I think this stands for axis minimum, probably. And this will give us for X at axis 0, the minimum. So for each dimension, the minimum value in X. And then we're going to also get NP a max, X is 0, so the maximum for every dimension. And those 2 values that we're passing here, those are the boundaries for the uniform distribution. So for every single centroid, we're going, or for the centroids that we generate, on every dimension, we're going to keep the coordinates of the centroids within the min and max of this respective dimension. I hope this makes sense. And then we're going to say, in general, the size is just how many centroids do we want to have, k, because k clusters, right? And X shape 1. So we want to have, X is the data that we already have. Those are the data points. One data point has a certain shape. And this shape, the same shape, is the shape of a centroid. So a centroid is just a data point, but it's a centroid, right? So we treat it differently. So just to make sure that you understand this, it's important, it's intelligent to keep the centroids within the boundaries of the data, because it doesn't make sense if I have, again, in 2 dimensions, if I have all the data here, right? And I initialize a random centroid down here. Now, it will probably find its way into the data, but there's no reason to do that. I can just keep it in here by default, right? So that's the idea here. We're generating that for every single dimension. We consider the minimum and the maximum of that dimension. So for the x-axis, for the y-axis, for the z-axis, and for the 5,000 other dimensions that you potentially have, you consider the min-max of this particular dimension. What we do next is we iterate for placeholder that we don't need to name in range max iterations. And what we're going to do now is we're going to create our cluster labels, so the y's. Even though it's not a target variable, but we have now the y labels for all the x data points. In the beginning, an empty list. Now, for every data point that we have in x, what we want to do is we want to compute the distances between every single data point and all the centroids. Now, we haven't talked about the distance measure mathematically yet. So how do I actually calculate the distance? Now, we just drew the lines here, but what are these lines? So, wrong color. If I have a coordinate system here again in 2 dimensions, and I have a point A here and a point B here, I think it's quite easy to understand, if I have x here and y here, how to calculate this distance here. This distance here is just, this is the Pythagorean theorem. So we have the delta x, the delta y, or it's a and b, and we have c here, and we know that c is the square root of a squared plus b squared. This is just the Pythagorean theorem, and this results in the Euclidean, so this is the Euclidean distance that we're using here. The Euclidean distance measure tells us how far is a from b, what's the distance here, And we do that by taking the x difference and the y difference, squaring those, summing them up, and then taking the square root of that. This is how we do it in 2 dimensions. In 3 dimensions, the process is the same, and I hope I can draw this somehow intuitively here so that you actually understand what I'm talking about if this is not obvious to you. So x, y, z. What we do is we have a data point here. So maybe it's just 1 in the y direction, maybe it's 3 in the x direction, and 0 in the z direction. Then I have a point here, which is maybe 0 on the x-axis, then it is 5 or so on the z-axis, and then it's also 10 or so on the y-axis. So how do we get the distance between those 2 points? Well, we do the same thing. We just we take the difference. I'm going to now, I don't know if that's correct, delta x, the difference in x between those 2 points. So how much do I have to go into, or this is actually y, how much do I have to go into this direction? How much do I have to go into this direction? And how much do I have to go into this direction? We square all of these and we take the square root. So it's actually the sum of these differences. So of AI minus BI, where I is the dimension, we square the differences here, we sum them up, and we take the square root. That is the Euclidean distance in every dimension. So I is 1 up until n for n dimensions. That is how you say that, how you write that. So yeah, I hope the notation doesn't confuse you too much. It's basically the same thing. If I go 5 steps into the x direction, that would be delta x. That would be maybe the first dimension. So a in the first dimension, which is the x-axis. How much do I have to move to b? Maybe -5, square that, and sum all the dimensions up, and then take the square root. This is the Euclidean distance. So actually what we're going to do here in Python now is we're going to say, we're going to define a static method, so we don't need the self keyword, it's just a calculation, Euclidean distance between data point and centroids. And the idea here is to actually not compute the Euclidean distance between 2 points, so not one data point and one centroid, but one data point and all the centroids. So actually we're doing return NumPy square root. Remember, again, the formula, what was it? Square root of the sum of the squared differences. So the first thing is square root. So if you call it in functions, the first thing you actually do is you do the subtraction. Then you square it. Then you square the difference. Then you sum all these squares up, and then you take the square root. But when you write it in Python, you first do the square root in terms of what you mentioned first. So we do the square root of what? Of something that's already calculated inside of this. So np.sum of what? Of the squared differences. So centroids minus the data point squared. This is summed up on axis 1. And then from this sum, we take the square root. This is how we compute the Euclidean distance if we have one data point and n centroids, no matter how many they are. And this is just a thing in NumPy, right? If you have 500 here, so 500 vectors here, or 500 points here, and then you have 1 point here, you're going to just subtract the same point from all the centroids. So you're going to calculate this for all these centroids. This is just how NumPy is implemented. So what we want to do here now, remember we are in the fit function in the loop for data point in x. What we want to do is we want to calculate the distances between the centroids and this data point. So k means clustering dot Euclidean distance. Let me just make sure I'm not blocking this here. Euclidean distance between this particular data point we're looking at right now and then self.centroids. And then we assign a cluster number to it, and the cluster number that this point will get is the arcmin. So np arcmin. This function returns to us the index of the smallest value. So this, what this line here returns to us is a list of distances. So we have now a list or a NumPy array with the distances between this point and all the centroids. And I want to know which centroid has the smallest distance to this point. And I want to know the index of that centroid, of the index of this distance here. So I take the arcmin, the minimum value, which index does it have in the distance list. And this is my cluster number. And this is what I append to y, the cluster labels. All right. And then we're going to turn I into a NumPy array. And that's it. So this is now the first step that we talked about. This is actually just what we did in the beginning this year. We randomly initialized them, and now we assigned every point to a centroid. This is all we did up until this point. Now what we want to do is we want to readjust the centroid position. So we want to reposition the centroids based on these labels. And we do that by saying cluster indices equals empty list, and then for I in range self.k. So for every cluster, what we're going to do is we're going to say cluster indices append np arc where, and basically what we're doing here now is we're preparing for the next evaluation. So what we have in y is now for every point in x, which cluster does it have? But we also want to know for each cluster, which indices belong to that cluster. So we say cluster indices, arc where, so give me the indices where something is true, where y is equal to I. So this is how we do that. And then we say for, or actually we say cluster centers. And here we now recompute the cluster centers. So we get an empty list and we now reposition the centroids. So we say for I indices in enumerate, so that we have the I, cluster indices. And we say if the length of the indices is 0. So because sometimes you might have, if you have two clusters, obviously, but you use 100 centroids, some of them are going to just have no data belonging to them. So they're going to have empty cluster indices. Yeah, so you will have, basically what we have here in the cluster indices is we have a list of lists. So we have for each cluster, which of the data points belong to that cluster. So for the first cluster with index 0, we're going to have a list of all the indices in X where for the data points that belong to that cluster. Some of them might be empty because some clusters might have 0 members if we have too many clusters, if k is too high. So if that is the case, we're just going to say cluster center will stay the same. So cluster centers, we're going to just append to it what it already is, centroids I. Cluster centers is basically just a new centroid. So if there is no member, we're not going to reposition it. We're just going to take the current centroid and set it as the new centroid. Same thing. Otherwise, cluster centers dot append, and we're going to take the average position. So np mean of x indices, so the indices of the elements belonging to that cluster, take all of their positions, compute the mean position, and we do that by specifying axis equals 0, and take the mean, so the first value here, there you go. This is our new cluster position. And now the only thing that we need to do here is we need to say if np max self centroids minus NumPy array cluster centers, if the difference here is less than 0.001, for example, you can choose your own threshold. If that is the case, we're going to break. This basically just says, okay, if the difference between the centroid position as it is right now and the new centroids, if the maximum difference on all the centroids, so if there's no centroid in the whole list that has more change than this, we can just break. And we can just say it's done. Otherwise, we're going to do it, we're going to just say self-centroids equals np array of cluster centers. So we reposition the cluster centers. There you go. And then finally, what we get as a result here is y, the cluster labels, once we're done. All right, so that is the full implementation. Let's see if it works. Let's see how it works. We're going to say for this random underscore points equals np random dot randint between 0 and 100. And we want to have the shape 102. So we want to have 100 two-dimensional arrays so that we have two-dimensional points. And we're going to say k-means equals k-mean clustering. K-means clustering. K equals 3, which is actually the default. And the labels is now going to be equal. The labels are now going to be equal to k-means fit on the random points. Now every point has a label. And all we have to do now is we have to visualize this plt scatter random points, plot the x values, plot the y values. The color is going to be determined by the labels. And then we also want to scatter the centroids. So k-means dot centroids x values, k-means dot centroids y values, c equals range length k-means dot centroids. So for the colors, and then, oh, actually now I'm blocking again with my camera. And then we're going to say marker so that we can distinguish them is going to be this star. And we're going to say the size is going to be 200 so that we can actually see the centroids clearly. What's the problem here? This is rand int. I think I'm using one bracket too much here. There you go. So now what we have here is we have data points. Those are the cluster centers, and this is the clustering result here. This looks reasonable, and every time we run this, actually, we're going to get a different result. So, because we also get different data points, and also k-means can have different results in general. So you're not always going to end up with the same clustering. Yeah, so that's that. What we can do as well as we can use scikit-learn to generate data. Now, the implementation is done. We didn't use scikit-learn for the implementation, but we can use scikit-learn to have a data set that we can play on. So we're going to actually, if you don't have it, pip install scikit-learn. I have it in my case, and then we're going to say from sklearn.datasets import make blobs, because this is actually a function that creates data that is well separated. So we can say data. Or actually, we can keep the name random points, but we're not going to generate it like that. We're going to say make blobs, and we're going to say n samples 100. We want to have 100 data points. We want to have 2 features, 2 dimensions. And actually, we want to just get the maybe we're going to say here data equals. We're going to say data equals that. And the random points without the labels, because what this function does is it generates the data points and it also generates the classes, the correct classes. We want to actually, we want to only have the data points. So we're going to say data 0 is going to be the data. And in this case, we only get 2 blobs. This is actually what we wanted to do. I don't think so. Let me just see here. Make blobs. I think we can. Is there a parameter for this? Let me just see in the function here. Centers shuffle. Number of features. No, this is a different thing. I think maybe the centers. Maybe centers equals 3 will do it. Yeah, there you go. So now we have blobs with 3 clusters. Or do we? I don't know. Yeah, looks like it. Or maybe it's just random. I'm not sure. But you can see the clustering works. This is the important thing. It doesn't matter how to make blobs function works. You can see that our clustering finds reasonable clusters, probably the optimal clusters. And we can actually confirm that this is the case by computing something called the ARI score, the adjusted random score or randomness score. So the reason we have to use a specific score for this is because so let me just show this to you. If I print random points, or actually data1, we're going to get the actual labels. And I can also print the actual labels that our k-means clustering generated. And you can see, in this case, this is a good example. I think all of these points are exactly the same, but they have different values. So 1 is 2, and 2 is 1, but we can see that all 1s are all 2s here. So the clustering is correct, we just use different names. And if we want to consider, if we want to take that into account, because if I just say now, okay, are the labels equal to the data, I will get a terrible score even though the clustering is exactly the same. Because it doesn't matter if it's called 1 or 2, it's the same. So that's the important thing. And for this, we can actually say here from sklearn.metrics, import the adjusted rand score. And we can say here ARI equals adjusted rand score for data1 and labels. And when I close this here, oh, we have to print it, of course. Okay, in this case, it's 0.5, 0.77, 0.46, 1. In this case, 1 means it's exactly the same. All the clustering is exactly the same here. 1 again, 0.57, and so on. 1 again. There you go. So this is how you implement k-means clustering from scratch. I'm going to go through the explanation one more time in a faster way here. So we initialize the centroids randomly. For each dimension, we consider the range from min to max. We generate k centroids. We have an empty list of labels. We go through the data points. We calculate the distance between every data point and the clusters, or the cluster centers that we initialized randomly in the beginning. We assign to each data point the closest cluster, the closest centroid, and we then reposition the centroids so that they line up exactly in the middle of all the points that are assigned to this cluster. And we do that all the time so that the centroids get closer and closer to the middle of the cluster, and the data points then are assigned, of course, to the centroids. That's the basic idea. And we use the Euclidean distance, which is just like the Pythagorean theorem in n dimensions. So written like this mathematically here. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and bye.